10,700 fires. The fire brigade responded to 10,700 fires in properties in London last year. Now, this number's coming down year on year. And 10 years ago, this was 25% higher or so. That's because for every one fire that's attended by firefighters, 8 more properties are surveyed and the risk is evaluated by firefighters. But how to decide where to send the firefighters to do this? Well, this is the goal of my project, to determine this risk and to evaluate it. But there's a problem. London is complicated. The fires are distributed in London in a highly non-uniform fashion. And this makes saying where to distribute these fire safety resources a really complicated thing to do. But there's an even bigger problem, which is that London is constantly changing. So how does the fire brigade stay ahead of these changes in London? Well, let's answer this question by considering first a small part of London, a small part of south of London, the borough of Lambeth. So in Lambeth, as a little brother of London, if you like, fires are distributed in this highly chaotic fashion. And what we want to do is take external data sets and correlate them with this geospatial distribution of fires to see where we can find these correlations and therefore which data sets we can trust to do this. So we start with some Experian data, some credit data, and we try to correlate the affluence of different areas, different wards, with historical fires. And what we see is there is some correlation, but this correlation is weak at best. We can play this game with tall buildings, and we can say, okay, well, the prevalence of tall buildings and the tallness of these tall buildings, that also correlates at best weakly with historical fire data. Again, commercial properties, well, this correlates even more weakly. Rental properties, the correlation is decreasing. Energy efficiency is basically not really very well correlated at all, and the proportion of flats within any given ward is of vanishing significance. However, it's not all doom and gloom, because within each of these single data sets, it contains a key, it sort of contains a clue to the overarching problem. And while no single data set emerges as the obvious solution to be able to predict where best to deploy firefighter safety resources, when we add them all together and we combine them to use them in some sort of predictive model, we have way better results. Now, for any model, it's important to be able to test it. And to test it, you have to use an unseen data set. And what we did here is we said, okay, well, let's just take data, building data and demographic data, and say the subset of data that we know a priori for whom there was no fires, well, we get that right about 66% of the time. When we know a priori there has been a fire, we input these 2 parameters again, or rather it's actually rather a lot of parameters, but these 2 sort of categories, and we are able to correctly predict around about 50% of the time. But the value of any predictive model is not so much in the scientific curiosity of training it, but rather it's in the deployment of this model. And what we do here is we take this model and we apply it to the most up-to-date data that we have. And we say, okay, historically, fires are associated with a number of risks. And these risks and these weights are embedded within our model. And this is how the training works. But when we feed it new information, as this new information becomes available, we're able to get a real-time, up-to-date prediction of where the fires are likely to be so we can best deploy firefighter safety resources. But really importantly, we built this from the ground up. We said, okay, for each house, what are the energy efficiency properties? What are the heights? And all this sort of stuff. And what we are able to do is project this prediction back down to a highly granular level and then say, okay, here is a map to a firefighter, here is a map, here is where we think the fires are likely to occur. So you can see that highly risky properties are often very embedded within low-risk neighborhoods. And this is a really valuable thing, because you can say to a firefighter, well, look, these are the properties that we think are the most important ones to target for the home inspections. And these are the properties where it might be less of good use of time to inspect them. But we can also project this back up to look at London as a whole again. And we can project this prediction on fire boundaries. These are single fire stations that are sort of roughly in the middle of each of these polygons here. And we can say, okay, at a glance, well, some fire stations are likely to have their work cut out for them, and some fire stations are not. And what we can then do and say, well, strategically, it would be better to redistribute our resources into the yellower areas rather than the bluer areas. But more explicitly, and this is the most important point, we can subtract from our prediction the historical fire data so that then we get some sort of metric of fire preparedness by fire station. And so you can imagine here, for an area that is blue, you say, okay, well, historically there have been lots of fires, but now we expect there will be few. But for stations that are red, you can say, well, historically there have been few fires, but we expect this to be a real problem area. And this will help firefighters to be able to understand where these risks occur, to be able to deploy resources ahead of time to increase this fire preparedness. So just to summarize, we built a model, and this is able to target a household level such that we can better understand how these risks occur and where exactly it would be worthwhile deploying these firefighter safety resources, and to ensure the preparedness of fire stations on a more global level. Thanks very much.